Okay, so I will be operating on a state omega, but I will also have the luxury of some public coins. I told you this. So the measurement simulation protocol has some public coins given to both Alice and Bob that are independent of the state. Okay, so this is so so I will use the public coin, is C public coins per measurement. C public coins per measurement. So C public coins per measurement. So when I toss C coins, I'm going to get an outcome. I'm going to get an outcome in 2 power C possibilities, right? If I do it n times, so it's going to be 2 power C times, because I'm doing n length simulation, right? I'm doing an n measurement simulation. So 2 power C. So these are so many possibilities of my public coin. So the idea is to take, say, 3 public coins per measurement. Uh, Public coins per measurement. Uh, then if I make n measurements, I will have 3n public coins. So each fellow will be giving me 1 bit. So I'll have 2 power 3n, right? So C is 3. So that's so these are the number of public coins available to both. So whatever Alice sees, so it's going to it's random, but whatever Alice sees today, Bob will see the same thing that day. Okay, so that's what it is. So this is independent of the quantum state. So how do we model this? So what is the state? The state is so you have omega, and then you have public coins. So public coins are represented like this. So this is the joint state and the public coins. So you're getting these public coins, right? So you're getting NC public coins. And then there is a state that is given to you. So what is this entire joint quantum state? Well, the public coins are independent of the state. So what is the distribution of these public coins? Well, it is just 2 power NC, each with probability 2 power n, each with probability 1 by 2 power NC. This is, it remains in state K. So K equal to 1 to 2 power NC with this probability. So I'm just coupling the two. That's all I'm doing. Okay, so that is your that is the state on which you will do your simulation. Okay, so I'm going to define this as, I'm going to define this as omega k. Okay, there's a k at the bottom telling you that there are some public coins with the state omega. Okay, so omega k 1 by I might use k and 2 power nc interchangeably. Okay, capital K is the range of your public coins. Little k denotes a realization of the public coin. So I can say k equal to 1 through capital K. So this guy is essentially 2 power nc omega tensor outer product k. So that's my state. Okay. Now I told you what is theta mk, right? So theta mk. So if the, okay, so let me explain. So let me define this. So remember this. Sk power minus half. So it's a beast, but don't worry about it. Just kind of stare at it. And I told you why it is this way. I kind of explained what is the intuition behind this definition. It comes exactly coming from the classical likelihood nature, and that's why I call it likelihood POVM. So this is k. Sorry, m 2 power nr. So m is the number of outcomes of each measurement. So remember, I have a bank of measurements, theta 1 to theta 2 power nc, or I can also call it theta 1 to theta k. If I look at a particular POVM in that bank, this has 2 power nr outcomes, and I call m as 2 power nr, m for message, k for public coins. Okay, so this m has to be conveyed to Bob. This k comes, nature gives this k. So Bob has essentially m and k. From that, he has to do something. Okay. So what is theta k? Theta k consists of theta mk, m equal to 1 to 2 power nr. What is theta mk? That's what I'm writing about. This is 1 equal to m to 2 power nr. Then there is a null kind of a guy, just to ensure that the space is completed, minus pk. Okay. What is sk? Sk is just normalization. Just normalization. 1 by no, it's just summation. Just summation. M equal to 1 to 2 power nr root omega lambda xn of m comma k root omega divided by trace 2 power nr trace omega xn of m lambda of xn of m comma k. Okay. So what is happening? So what did I tell you? So you are getting these public coins. So I have this bank. So again, I'll write a picture. So theta 1, theta 2, theta k. So each fellow consists of theta 1, 1, theta m comma k, theta 2, 1, theta 2 power nr comma 1, that is m comma 1, theta 1, 2, theta 2, 2, theta m 2, theta 1 k, theta m k, and the last one is theta capital K, which is theta 1 k, theta 2 k, all the way into theta m k. Okay, so this is your bank. So this is one POVM, this is another POVM, this is the last POVM. So the idea is, so you get these public coins. So these public coins are essentially, think of k, always remember k equal to power n c. Okay. So you get these public coins. So these public coins could be something like this. Okay. Whichever this indexes, you go to that POVM and you perform that measurement. Okay. So this is what is the protocol. So how do we model this? So I'm going to model this as follows. So what is the state including the public coins? I told you this is this 1 by k omega tensor kk, right? Again, see k as 1 2 power n c. So this is what you state. What I will do, I'm going to define a big POVM. See, I have defined a POVM on this, right, on omega, when my state is k. Okay, why don't I define a big POVM operating on the entire object? That's all I will do. Okay, so you see, so the way it works is you stare at k with your eyes, and you operate theta mk, right? You operate theta k, right? You look at k with your eyes, and you operate theta k. So in some sense, your eyes is doing a measurement. So I can write a big measurement, right? So that big measurement is as follows. So theta is my big measurement. I will make the measurement theta mk if I see the public coins in the state k. Okay, that's what this means. So now I have k belonging to k. So I am doing a measurement on the classical register also. And whatever that gives me, I'm going to do that corresponding theta mk on the particle space. So that's the idea. I'm just, this is just formalization. No big deal. Okay, so this is your 2 power nr. So this is 2 power nc. This is 2 power nr. So math looks crazy, but the intuition is very clear. So you look at public coins, you make that measurement. So now you can show that theta mk tensor kk. So if I add, so now I sum over k and m because I have now so many operators. I've clubbed up the two. So the idea of seeing this classical register and doing this measurement, I just clubbed it as a big measurement with so many operators. This you can show is IA tensor n tensored with IK tensor n. I mean IK, that's it. Okay. So now there's my big measurement. So where does theta operate? So E theta operates on L of particle space coupled with the public coin space. Okay. And it is going to throw out, what is it going to throw out? It is going to throw out the particle as is. Sorry, not as is, but obviously it's going to throw it out. The particle space will be there. It's not going to squish out anything. So it's going to leave the public coins as is. But for every outcome, it is going to give another outcome. So I'll explain this. M tensor HK. Let me put HK tensor. Okay, let me explain this. Recall, when I have a measurement lambda, right? What is E lambda going to do? E lambda operates on S and it is going to put out root lambda x S root lambda x tensor x x. So for every, so whenever I have a POVM with an outcome set, so you think of any, okay, so think of any POVM, let's say the POVM is gamma, and it has say an outcome set little o, I mean capital O, so O belongs to O, this is my outcome set, so this is my POVM, okay. Whenever I have this POVM, E gamma is defined as, when I operate on S, I'm just going to do root gamma O S root gamma O tensor the outcome. So this is my definition for any POVM gamma with an outcome set O. Okay. So now I have a POVM with outcome set M comma K. Okay. So that O is like M comma K because this is my outcome set, right? Because every element of your POVM corresponds to an outcome. Now I've coupled the public coin and everything. So it's going to throw out K comma M. That's what this is. So this theta operates on this space, leaves that space as is, and it's going to throw an outcome, just like in here. Okay, just like in here. So, so what is theta? So E theta operates on S, and it has to do, it has to do this theta S theta tensor K K M M, right? That's really what it has to do because that's your outcome. Yeah, so this S now, S lives inside L of HA tensor HK. So I have not, I have put both of them. Always, this is kind of the way it works. Okay. So what is this guy? What is this? So what are these objects? So I'm going to write this down. So E theta operated on an element that has both the particle and the public coin. That is your S. S represents that. You do the following: theta mk root of the rank 1 operator kk, right? That root of rank 1 operator kk is kk itself. So this operates on S. It's a big S because it contains both the particle and the public coin. Root theta mk tensor kk. And outcomes, the outcome which is k tensor mm. Okay, there is one HK space here also, and there is a new HK space created and a new HM space created by the outcome registers. Okay, so that's your E theta S. So now let's start to let's kind of start to write down the different elements of the protocol. So the first stage, so you have so what is your initial state space?
Hello.
Yeah.
Can you just show me the definition of the theta once more? I'm just confused why there is a root theta mk tensor kk.
Yeah. See what
Why
is
not?
yeah, I'll explain. See, when you have an outcome, when you have a POVM O, right? Then when you operate it on S, what do you get? You get root gamma O S root gamma O tensor O. Do you agree with this?
Yeah.
Okay. Now I mean summation. Okay. Now what is my gamma O? My gamma O is something like this: theta mk tensor kk.
Okay, that's how you're defining it. Okay,
Yeah.
fine.
So
Now
when I
it's
yeah, good. Okay. So let's continue. So the initial, so this is important. Initial, I want you to kind of understand this. I'm going to give you an exercise. Initial state space that you start with in the simulated protocol, right? So you have a particle, you have a reference space, tensor n, right? There is a particle space. Sorry, I should not write like this. So HR tensor n. There is a particle space, and there is a public coin space, right? Obviously, when you have a particle space and a public coin space, your reference space also should contain a copy of that public coin space. So that is why this is my initial state space. So remember, whatever state my particle is in, I should copy that in the reference space, right? At least. So now my particle really contains this whole thing. So I'll have to copy both. That's my reference object. When I make the measurement E theta, so E theta operates on the second component. So it's actually I. So what is my operation? My operation is I'm keeping the reference space as is. So I have an IK tensor E theta. So E theta operates on the tail HA tensor HK, and it throws out something. What does it throw out? So after the first operation on this state, I end up getting on a particle in that space. End up getting the reference space will remain as is. So will the reference public coin space. The particle space will remain as is. That's how I've defined it. I'm going to trace it out later, but it's going to remain as is. The public coin also will remain as is, and then they will come out a outcome K and a measurement. Sorry, a message M. So these are your outcomes, outcome space. So the tails will be the outcome space. Now, then what you do, I told you, you trace out the particle space. So now your next operation will be tracing out the particle space. You will keep the reference IR tensor IK. So that is, so that first IR tensor IK hits on this guy. Okay, that remains as is. Then you trace out the particle space. So trace out A. You also trace out the public coin because you don't need it. You have a copy of it. You have a copy of it, which is going to go to Bob. Okay, so so you trace out the particle space, and then you keep the outcome space as is because you want to communicate. So Bob has to be given the public coin. Bob is given the public coin. So we'll try to kind of write it mathematically. So the K that comes out, really you will give it to Bob, and the M that comes out also you'll give it to Bob. But you are not going to charge yourself for this K because that's given by nature itself. I mean, just kind of agreed. So you're not going to send it on that wire between Alice and Bob. Remember, there is this. So if you go back to this scenario, there is a blue wire between Alice and Bob, and in that blue wire, the M goes, and the K goes through the red, from nature. Okay, good. So that is your. So this is. So what is the state space now? So the state space now is you have traced out certain things. So those guys are gone. So you will have the first reference space as is, and nobody has access to the reference space. It remains as is. The next two that is the blue, trace A and trace K kills these two. So I will end up with HK tensor HM. So that is the state space post all of Alice's operations. Okay. So now what happens? This K and M is given to Bob, and Bob has to do something on that and pull out a Y, pull out an XN, right? Because finally you want to simulate. What do you want to simulate? You want to simulate this root omega lambda xn root omega tensor xn. You can't just keep the x, I mean k or something. I mean k and m are I don't know what it is, right? He has to somehow map that k and m to the potential outcome that the outcome that that should be coupled with the state of the quantum register. So he has to somehow map that to x, map that to an x space. And the mapping is very simple. See, what have we done? Remember, I told you we have kind of partitioned our outcomes, right? I mean, only the typical outcomes really. We have partitioned that into, so if you go to the kth, POVM, and you get the mth message, that gate contains x of n comma k comma m. That's how I built my POVMs. Remember, what I will do, Bob will do something very simple. If he sees k comma m, he will display that x of n comma k is the outcome of the measurement. That's it. I mean, these xn's are all inside xn, right? So it's a valid outcome. I mean, yes, it might be screwed up, but I mean, he can always say that the outcome is xn comma k comma m. That's what he'll do. Okay. So what he is doing, he is staring at the register km, and he will display out xn of k comma m. Right. Now, since we are all in this kind of a measurement language, we should write that also as a measurement. Our process also should be written as a measurement, where you look at k comma m and you throw out xn of k comma m. So that also is a measurement at the Bob's end. Okay. So what is the Bob's measurement? So Bob will do a measurement. His measurement will have operators, right? So I'll call that delta for decoding. So delta, what are the outcomes? So whenever I write a POVM, right, I'm going to write under the subscript of the operator, I'm going to write the outcome of the operator. Okay. Under the subscript of the operator, I write the outcome of the operator. So delta xn, so xn is my outcome. It operates on k comma m, right? It operates on this space, so it better operate, its operators must operate on that. So this is what my POVM operator is. K tensor mm indicator function xn equal to xn of k comma m. So whenever xn of k comma m is xn, you throw out xn. That's in English, that's what this measurement is doing. And sum over all k comma m, all those. So how do you see this? So the way you should read this is, when do I throw an outcome? When do I say that the outcome is xn? Whenever I get a k comma m whose entry in my table is xn. That's how I should read this. So whenever sum over all k comma m, when the entry in my table is xn, then you throw out xn. That's how we should read this POVM. So just doing that, all that is doing is just that I told you. You can show, I mean, this is an exercise, you can show that when I sum over all outcomes, I get identity over k tensor im. Okay. So where is delta operating? So E delta will take you from your k, it takes you from the space in which your public coins and your message lives, and it throws out, well, it's going to remain, it's not going to trace out the with our convention, it's not going to trace out what it sees or what it operates on, and it's also going to throw out a xn. And so so clearly, if I take s, where does s go? It goes to root delta xn s, root delta xn, tensor xn. That's all. That s happens to live in the classical space, a k cross n classical space. I'm just writing everything explicitly so you can see the pattern as to what's going on. Okay. So why did I do all this? So I'm going to copy this and continue from here so that you know going on. Copy. So here I am. So again, kind of a recap. Initial state space, you start with that. Alice operates E theta. You get a big space. Then you trace the particle out. So now you are left with HR tensor HK tensor HK tensor HM. This is the public coins in the reference space, which nobody can touch. Okay. And Bob only has K comma M, so he has to better operate on that. He can't look at the reference space or anything. So he is going to, so what is the operation now? So the operation now is IR tensor N, tensor IK, tensor. Now Bob has done the E delta operation, right? So this is E delta. Okay. What will come out? Well, nobody touches the reference space. Nobody touches the K space, I mean the reference space. The measure, I mean, our convention is that when I do a measurement, that original space remains as is. We're going to trace it out after that. And then I'm going to have the new xn coming out. This is really my juice, right? So somehow we need this guy and this guy to be what it should be. That's the whole goal. So we have to trace out the rest of the things now, right? So our interest is only if we had done the original measurement, we would have only had this guy and this guy, right? So the rest of the guys should just vanish now, right? So I really want to see that those two guys are preserved. So this is just the last is bookkeeping. So IR, the reference space is as is. Now I trace out the public coins in the reference space because who cares, right? I mean, who cares? I don't want that. I don't want to measure. I don't want to be. I mean, that's not even there in the original guide. So I'm going to trace that out. I'm also going to trace. So whatever public coins that Bob is given and whatever the message that Bob is given, who cares? I mean, trace it out, right? I mean, finally, I'm only looking at. I mean, have I simulated the measurement? That's the question. So I keep the xn space. This is my final measurement post all of this. Okay. So this is very important for you to understand, and I will stop and I will ask you if you don't understand, and I will explain. This is F1. This is the first F1 map. This is the second F2 map. This is the third F3 map, and this is the 4F4 map. So the simulation is working on. So last is F4. Previous to that is F3. Previous to that is F2. Previous to that is F1. And this is operated on phi omega k with the public coins. Very important to understand. What is omega k? What is omega k? Omega k is the entire particle without the purification is 1 by k, the particle remaining as is with just independent random bits k and k. K equal to 1 through capital K. This is my thing on which I simulate. So I'm just using, so just see, I mean, I'm consuming this public coin, right? I'm just taking it, using that to do some measurement. Here's my measurement. I'm giving it to Bob. I mean, really, this giving notion is just, Bob is given that. I'm not using my wire to send that. And Bob is just going to use the K and the M, and then he's going to throw it out. So the public coins are gone. It's consumable. It's extremely important for you to understand this. And if you don't tell me, we will stop, dig in, and I'll explain again. Okay, great. At least you claim you understand. Okay, good. So what is, okay, so this is my simulation protocol. What is my original measurement? Remember my original, I'm going to call it E. So I'm going to write it in this language itself so that, it kind of makes sense to you. So initial space, well, I don't have any public coins there. So this is the original measurement, the analysis of the original measurement. So initial space, what is my initial space? Well, really there is no public coin. It's all very simple. So I have the reference space, HR tensor n, and I have the particle space. That's all, HA tensor n. And what do? I operate IR tensor E big lambda. This is what I operate. What do I end up with? HR tensor n tensored with the particle space remains as is, but I have done the measurement and the outcome registers will live in their own space. This is lambda xn. Okay, I mean sometimes I call this lambda xn or lambda x tensor n. Same. Okay. Next, what do? You trace out the particle. That's all that's happening in the original measurements. Very simple. Trace out A tensor n, and you keep your register as is. So I end up with HR tensor n tensored with HX tensor n. And I didn't write this. This is the last step after all this. So maybe it's good to do this. So give me 1 second. I'll push this down a little bit. And I'm going to push this up a little bit. And sorry, push this down a little bit. And after this final F4 measurement, right? What is my final space? I have the particle. The public coins in the reference has been traced out. The public coins that Bob sees has been traced out. The message that Bob sees has been traced out. I will just have I of x tensor n. So that means now I'm in a position to compare with the original thing that I got, right? So what am I doing? So let us call this E map, E1, E1, let's call this E2. So what am I doing? I'm looking at this object. E1 followed by E2 operated on phi omega without any public coins minus F4 follows F3 follows F2 follows F1 operated on phi omega k. Public coins are there, but in as consumables and used off at the end. This is what I'm interested in. Okay, cool. Now I'll do a small trick. Okay, I will do a small trick because it turns out analyzing this, I mean even characterizing this object is extremely complicated. Okay, you have designed your POVM and you're operating on the space. It turns out analyzing this is very complicated. So the POVM that I have constructed here is actually a very simple POVM. I mean, it's one of the simplest POVMs one would think of. You know, uh, if you know a little bit of like information processing, statistics, or likelihood estimation, detection. I mean, the people who work on these problems are all quite strong in this. So finding this POVM is not difficult. But why? I mean, if you read Will's paper, why he does not analyze this POVM is because working with this object on the right is extremely difficult. Whatever you get, it has a very involved characterization. You don't know how to show that these two terms are close. Okay, so I will do a fudge. Okay, so that's kind of why Will's paper is that complicated, and the proof that I'll give you is slightly simpler. It turns out that knowing this, I mean, knowing the theta POVM and is not difficult. I mean, you can write that down, but you can't analyze it. And how do you analyze it? So that's what I'll be showing you. So I'll do a small trick. So can I say, okay, why is the following true? Tell me why is the following true? So why is this true? So what have I done? I've taken the argument to which the argument that the F applies on, change that argument. And I add a term in the second term. Why is this true? See, these kind of questions are asking like, yeah. So you should kind of have, I mean, it's okay, you may call it measurement compression, but this is something we did in the very early in the distance measures. Why is this true? So let's go step by step. Okay, first, just is the question clear to both of you? Just say
Yeah.
yeah. Okay, why is this true? I'll tell you why is this true. So see, if I have two CPTP maps, A and B, two CPTP maps. So A operated on say rho, some state, minus B operated on some phi. Okay. Can I write this as follows? Can I write this? A operated on rho, so CPTP maps, both are CPTP maps, minus B gamma plus B gamma, so not less than. You can always add and subtract, no problem with that. B phi. So what I've done, just added, subtracted B gamma. That's all I've done. Now I'll use the triangular inequality of the operator now. So can I say this is A rho minus B gamma plus B gamma minus B phi? This is just triangular inequality. Okay, next, remember the following. What do CPTP maps do? So suppose I have two states, gamma and phi. How does the distance between the states compare with the distance between their outcomes when I pass it through a CPTP map? How are these two compared? And I give you some intuition for this. See, CPTP map is like adding noise. It's making it more uncertain, right? So if I have two distributions and I add the same noise to those two distributions, then they become lesser easy to distinguish. So if I have two distributions P and Q, right? Suppose I have a register and somebody inputs a random number either through P or through Q. Okay, so somebody's input a random number. That random number is sampled either through P or through Q. And he asked me, was it sampled through P or was it sampled through Q? Right? I have some ability to distinguish. But suppose somebody adds some more noise to it and then asks me to distinguish between P and Q, my ability here is much weaker because it's got mixed with some more uncertainty, right? So that's what this is. So your ability to distinguish between two states, gamma and phi, reduces if they are perturbed through some operation. So if it is harder to distinguish B gamma and B phi, so that means they must be closer, right? So that means this. So gamma minus phi is going to be the distance between gamma and phi is going to be more than the distance between B gamma and B phi. Okay. So that tells me if I go ahead, so that tells me that, so let me copy this as is, paste. So this guy, so this is equal to, this guy is lesser than, I keep the first guy as is. Looks a weird object. I mean, I was supposed to be operating B on phi, but now I was looking at, so look like an interesting thing, right? Because I was supposed to compare A phi and B, A rho and B phi, but now I'm going to compare A rho and B gamma, okay? And if I show this is, if these two, if I can somehow show that gamma is close to phi, and I can fudge for B phi, I can fudge B gamma. That's what's going on. Okay. So, well, I was supposed to operate my B on phi, but don't worry, gamma is not very far away from phi. So I'm going to operate on B on gamma, and I'll show B gamma is close to A phi. And I'll also show you that gamma is close to phi. So that way everything is maintained. So this is the trick. Okay, this is a very important trick. So I'm going to use this trick, and that's why. So this is my this is my rho. This is my p, and this is my gamma. No, I made a mistake. You look up. Wow. So essentially, what I've done is, well, phi omega k, I'll tell you is going to be close to phi gamma. So I'm going to operate my f on phi gamma. And I will show that phi gamma is close to phi omega k. So if I show you that both these terms are small, then whatever I was seeking is also small. That's all. That's all is the trick. I mean, sometimes one small thing will change the way it works. Okay, so we have two terms to deal with. We have to somehow. So I haven't told you what is phi gamma, but I'm telling you I'm not going to operate my f on my phi omega k, though that was what it was designed now. Okay, and I'll tell you what is phi gamma. So phi gamma, so recall the POVM. The POVM is given by like this, right? Theta is my POVM. So it has theta mk tensor kk. This is my POVM. Yeah. What is theta mk? I'm going to write it down because that's needed. Theta mk is as follows, right? Sk power minus half root omega. I mean, looking at this, you have no clue what this is, but like last time I told you, it is the px given y divided by summation px given y. That's really what it is. That's the only way you can understand this. 2 power n r trace omega lambda xn of m comma k. Okay, this is what it is. And otherwise, there is a I minus pk. Don't worry about this guy. That's anyway just m equal to 1 through capital M. What is sk? I'll write down sk because that's important. 2 power n r summation. I'm going to sum over all the m's. M equal to 1 through capital M. Root omega lambda xn of m comma k root omega divided by trace omega lambda xn of m comma k. I'm just doing normalization. That's all. That's my sk. Okay. What is the trace sk? What is trace sk? Let's do trace sk. Trace is linear. trace, well, the denominator is a scalar, so I can pull it out. So it's trace root omega lambda xn of m comma k root omega, it's an operator, divided by trace omega lambda xn of m comma k, right? Cyclicity of the trace, so I can say this is nr m equal to 1 to 2 power nr, trace numerator root omega, I'll bring it on the left. So root omega becomes omega xm of m comma k divided by trace of omega of lambda xn of m comma k. So this is 1 by 2 power nr summation m equal to 1 to 2 power nr times 1. So that is 1. Okay, so Sk is a good guy. I mean, he's actually positive semi-definite because look at, I mean, lambda xm comma k is positive semi-definite. So Sk is greater than equal to 0. I mean, it's a positive semi-definite operator. Trace Sk is 1. Okay. So it's a state. I mean, well, it's a state for whatever it is, right? I'm going to consider gamma. I'm going to define gamma as I'm going to mix these guys. 1 by k summation k equal to 1 through k sk tensor kk. Wait, let me explain. See, go back here. Let's go back here. I am substituting phi omega k with phi gamma, right? Where does, I mean, if phi omega k lives in India, then phi gamma also should live in India, right? I mean, you can't live in a different space. So this has to be in HA tensor n tensored with HK, right? That's what this guy lives in. What does this guy live in? This is essentially, remember, this is omega tensor kk 1 by k, right? So this is HA tensor HK. So my SK lives in HA tensor n, right? Because it's an operator. This lives inside HA tensor n, L of HA tensor n. So I have to couple it with something in HK. That's exactly what I've done. And I normalize it because I want gamma to be a state. So now clearly you can show that trace gamma is 1. So gamma is a state. Some weird object. I don't care what it is, right? It's some weird object. So now you know what is phi gamma. Phi gamma is the purification of gamma. Okay. So that is why. Okay. So the question is why, right? I'll tell you. I mean, there are two ways to look at it. See, when you so I'll tell you both a technical intuition and a kind of a scientific intuition. So the technical intuition is, see, look at the problem. The problem was when I operated this F1, F2, F3, F4 on phi omega k, right? I'm not able to characterize it well. And the reason is, if I look at F1, right? F1 is your theta operator, right? I mean, the theta measurement. You look at theta measurement, right? Sorry, I'm scrolling too much. So if I look at my theta operator, right? Theta has an sk on the left, sk minus half on the left, and sk half on the right. Okay. Somehow I want to get rid of that. I know that when I do a measurement, so when I do a measure, so look at what you, when you do a measurement and you trace out the particle. Remember, suppose I did that IR tensor. IR tensor n e theta. So when I operate the lambda, remember the lambda measurement. When I do this, and then I trace out the particle, I keep the reference space as is, and I keep the xn as is. What I get? I get root omega lambda xn root omega tensor xn. So what is happening? The operator is sitting in the middle, and the state with the root is coming on the outer edges, right? So look at this object. So if I can take my state as sk, then that sk will come and sit on the left, and the sk will come and sit on the right, and the two sks will get knocked off. The root sk will come and sit on the left, and the root sk will sit on the right, and the normalizations will go off, and I will just get the nice term in the middle, right? So that may seem a very technical intuition, but actually what is going on is that you are trying to, so what is sk? Sk, remember, is kind of the normalization term, right? So it is summation p x given y. That's what it is. Xn given yn of k comma m. It actually, this thing actually is actually very similar to pxn. Okay, so there is so if you know this has, I'm not going to go too much into this, but this is for somebody who is kind of working on this or reading this. I can explain how does this, how does the choice of this gamma come? Why does the, why do you know, why does, you know, why did I think about inserting a new phi gamma and then, you know, doing this step? Why did I think of this, and why did I choose my phi gamma? I can explain that in more detail to somebody, but that's what you do. So this is your gamma. Okay, you operate on phi gamma, a purification of gamma, and you operate on, so let me explain this. So what's going on? So I'm going to do this. So gamma, just going to define everything carefully. 1 by k summation k equal to 1 through capital K sk tensor kk. This is my phi gamma. Okay, phi gamma is some purification of gamma. Now I am studying the following. I'm going to study E1 tensored with, sorry, E2 tensored with E1 operated on the original state phi omega minus F4 coupled with F3 coupled with F2 coupled with F1 operated, I mean, preceding F3, no, following F3, following F2, following F1, operated on phi gamma, not phi omega k, which was what I was supposed I was asked to do. This is what I'm looking at. Okay. And what is gamma? Gamma is, so I'll write down all the terms and I will leave a homework here. So 1 by k summation sk, k equal to 1 through capital K tensor kk. And what is sk? Sk is 1 by 2 power n r m equal to 1 through capital 2 power n r root omega lambda xn of m comma k comma m. I might be looking the 2 root omega divided by trace omega lambda xn of k comma m. Okay, so this is what it is. So and what is f1? F1 is essentially IR, the particle space, and the public coins of the particle space, E theta. This is your F1. And what is theta? Theta is given by theta mk tensor kk, and I'm not going to write theta again. So all the terms I've written down, and what I want you to show is, I want you to show the following. F4, F3, F2, F1, I've told you all those characterizations. So I want you to show the following. So this is homework. I mean, it's a good homework on CPTP maps. It's a good homework on distance measures in concepts. So F4 followed by F3, following F3, following F2, following F1, operated on phi gamma. I want you to show a lot of kind of writing, but it's not that big. 1 by k times m, k m root omega the SKs disappear as I told you. Lambda xn of k comma m root omega by trace omega lambda xn of k comma m tensored with xn of k comma m. Remember, you will only have the reference space and the outcome space. That's all you will have. This is what you will get. Extremely good exercise to do this for the exam preparation. So show this. So that gets us. So remember, we are interested in this object. This is the first term in our two terms, right? We have already done this. Remember, we have already done this. Okay, so what am I stating at? I'm stating at the following. So I'm going to write the first term and the second term. The first term is the following: xn root omega lambda xn root omega tensored with xn minus this term which I'm writing about 1 by k times m k m root omega lambda xn of k comma m root omega divided by trace omega lambda xn of k comma m tensored with xn of k comma m xn of k comma m. So this is what I am after, and I will pause and I will let you ask me questions. Not difficult. It's just just calculation, literally calculation. But it gives you a chance to write down all the objects, understand the object, what's going on, what are densities, what are states, and then what are the maps, and then writing out everything, looking through this lecture. It's a very good homework. Not really difficult. Just literally calculation. But you will go and revisit the CPTP maps for this reason. You will go and revisit whether it's a CPTP map, choice cross operators, all of that. So it's not a bad. Okay. Question starts. Is it okay? I mean, model or that exercise. Okay. So now, what do you guys think this is? So I'll tell you. So
Something with the covering lemma.
yeah, this is actually the covering lemma in disguise. The covering lemma is just the covering lemma. So let's do it. Okay. So let us remember what the covering lemma says. The covering lemma says, suppose Px is a distribution. Suppose I have a set of x. I have a distribution Px, and I have a bunch of density operators, x belonging to x. And the ensemble average rho, the sigma, is Px of x sigma x. Sorry. Suppose I have this. I know rho tensor n is, if I just mix all the xn guys, then I'm going to get rho tensor n. This I know. But I need a huge number of states for this. And so what I do is, I know if I take some 2 power nr states, instead of taking all the rho xn's, I'm going to take only some collection. Okay. And I'm going to just mix over that collection. Okay. So rho xn of m equal to 1 through 2 power nr. Suppose I mix only these guys, then this is really small. It's almost very small. So write this slightly differently. So left side, what is left side? Left side I can write it like this, right? Pxn of, say, xn row xn. I mean, don't worry about the dummy variables doing the summation. Don't worry about that. Left side, I'm just writing it like this: minus 1 by 2 power nr m equal to 1 to 2 power nr. Row xn of m is very small. So instead of averaging on so many, I can just average on 2 power nr, and it turns out 2 power nr, r is s of sigma minus px of x, s of rho x. This is what we showed. If r is like this, right? Let's look at this thing. We will see that this is the covering lemma in disguise. Copy. Okay, the covering lemma in disguise. Why is that? Let us define. There's a row. So I'm going to define, instead of row, I'm going to define mu. Okay, so what is mu x? Mu x is the following. So I have a set x. Okay, same set x. I'm going to define my distribution px to be px of little x is trace rho lambda x. This is my distribution. Okay. What is my state? My state, okay, so that is mu x, mu little x, right? I have to define, define a set, I have to define a distribution on that set, and for each element in that set, I will give you a density operator. I'm going to define it as root rho lambda x root rho divided by trace rho lambda x tensor xx. This is my state. This is my mu x. Okay. This is my mu x. So what is summation px of x mu x? That is going to be summation over x. The trace rho px is trace rho lambda x, so that will cancel, and I'm going to get rho lambda x rho tensor xx. Okay. Now, what is going to be my so let's call this alpha. So alpha is my ensemble average. What is alpha? Alpha is my ensemble average. X belonging to x, root rho lambda x root rho tensor xx. Okay, that's my ensemble average. What does the covering lemma say? Well, alpha minus 1 by 2 power nr m equal to 1 through m mu xn of m. This guy is going to be closed if my r is large, right? What I will do, instead of this xn of m, I'll just double index it. I'm going to call it xn of k comma m, double index. Who cares, right? So just split it up into, if there are r bits, I'm going to split it into r, some 0.2 r as k and 0.3 and 0.8 r as m, right? So km. Okay, so I'm just going to write the same thing now. So alpha minus 1 by k times m equal to 1 through m, k equal to 1 through capital K. Mu xn of k comma m is small is what this is saying. If my km has some ratio, right? So so this is 2 power nr. So if I take the log of that, log km, I get nr, divide by n, I'm going to get r. So if this is of the order s of alpha minus px of x, s of mu x, do you guys agree?
Yes.
Yeah.
Okay, great. That's all this is. What is mu xn of k comma m? Let's write it down. 1 by km m equal to 1 through capital M, k equal to 1 through capital K. What is mu x? Mu xn. Well, mu x is sitting here. So it's essentially root rho lambda xn of k comma m root omega. It becomes root rho. I mean, you'll take the common out and then you will pull it out. Well, yeah, show this. I mean, it's not difficult. Trace omega lambda xn of k comma m tensor xn of k comma m xn of k comma m. So it's this, right? A C A tensor A B A is A square C A tensor B, CB tensor A square. Sorry, this is it. Because you're operating one after another. Just show this. This is coming from the tensor product axioms. So this is exactly what we wanted. So this is exactly what we wanted. So this tells us the covering lemma of one shot of the covering lemma. So what does it say? So if my log k m divided by n is greater than s of summation root rho lambda x root rho tensor xx. This is the ensemble average. I have averaged the ensemble minus trace rho lambda x. I'm writing it explicitly so that you know what's going on. S of root rho lambda x root rho divided by trace rho lambda x tensor xx. Okay, this is your so this is the von Neumann entropy S. This is the von Neumann entropy S. If this is greater, then you are in good shape. Then the first term is going to knock off, right? If you choose randomly, you can choose your. So what you have to do? You have to go to your xn space. That's your outcome space, and choose xn of k comma m uniform. I mean independently, randomly according to the distribution px, which is your trace rho lambda x. So it's giving you everything. All the ingredients are set up. So that's your first term. Questions, thoughts, ideas. I mean, yeah, it might, it might seem okay. How did this happen, right? But there is intuition. There's strong intuition, and slightly hard given the time to explain the intuition, but very strong intuition. It's just not the SK sitting on the left and getting cancelled. It's not that. It's more than that. But this is the idea. See, what is happening is, let me explain let me explain what's happening. See, the covering lemma is telling you, if you have a quantum state alpha, how do I simulate alpha? That's what the covering lemma is telling you. How many states do I need to simulate alpha? Okay. Why is this used in the quantum measurement? See, when you make a measurement, there is a state that gets created between the there's a state that gets created, a quantum classical state that gets created. It is a mixture of states. Okay, it's a mixture of, indeed, if this is the outcome, this is the state, that is the outcome, that is the state. It's a mixture of states, right? So your alpha, just like your alpha was a mixture of states, px of x mu x, right? Just like that, your post measurement state is a mixture of states. How many states do I need to simulate that post measurement state? That's the idea. And what is the minimum number of states do I need? So you just communicate that that is kind of your like your K and M. So how many states do I need to mix to be able to get to the post measurement state? Uh, and the covering lemma tells you, okay, these are the number of states you need to mix. That's really that's really where the covering lemma is coming. It should make very good sense because in a post measurement state, see, remember, even if you don't think of the reference space, right? So when you make a measurement row, when you make a measurement lambda x on row, you are going to get the state. So let's say even mk, let's say mk also, right? You're going to get mk row mk dagger by trace row mk dagger, mk row mk dagger, mk row mk dagger, mk row mk dagger with probability trace mk row mk dagger, right? So what is the post measurement state? It is a mixture of this ensemble. That's like your mu x, mu k ensemble with probability distribution trace mk row mk dagger. That's your probability distribution. And what you're getting is essentially this. You're getting, put the probability on the left, mk row mk dagger, times the state. What is the state? Well, there is a quantum part and there is a classical part. I'm mixing the state. Now, how do I simulate the state? Well, you don't need all the outcomes. That's what the covering lemma is telling. You don't need all the xn's. That's what the covering lemma is telling. You can take a sparse sampling of the xn's. So you can take a sparse set of outcomes and you can essentially simulate the entire state. So when you get a sparse set of the outcomes, then you can compress your measurement outcome. You don't need to, all those measurement outcomes are not needed to nature. What is nature doing? Nature is just going to sample from this ensemble uniformly and throw it at you. And you can also do that. I mean, if he's doing that, why can I not do that? Right? That's really the covering lemma is the quantum measurement compression is a beautiful application of the covering lemma, and it's all sitting in place. You can see the entire kind of the measurement and the outcome of the measurements and all of that come into play. Question starts. I'm still not done because there is one more term to remember. Yeah, I mean, you should go back and look at this video, and somebody is interested in covering lemma, they should go back and kind of look at it and then ask. Anyway, okay. So I have done one term. There's only one more term remaining. Okay, I have two options. Either I can stop now or take another 30-40 minutes sometime later and finish it. Let me know what you prefer. I will complete the entire syllabus because I'm finishing the covering lemma. I told you everything carefully. You just have one term. Just have this one term. We have done the first term. Just have this one term, and we know what is gamma. We know what is not here. Yeah, this is where we are. We have done this. This first term is now done. The term that remains is the blue term. We know what is gamma. Gamma is essentially the mixture of the SKs. Right? This is your gamma. This is your gamma. And you know what is the phi omega k? That's the mixture of the original state with the with omega. So let me just write it down and then I'll let you guys think about it. Want me to do it today, or do you want to finish? Do you want me to do it now, or do you want me to take another class? So so gamma is 1 by k equal to 1 through capital K, sk tensor kk. I've already pounded you many times with this as k. So this is k is what? 1 by 2 power 1 by m. Summation m equal to 1 through capital M. Root omega lambda xn of k comma m. Root omega divided by trace omega lambda xn of k comma m. Actually, this is not one step, but let's see. This is sk. What is phi omega k? Omega k, what is omega k? Omega k is just 1 by k k equal to 1 through capital K, omega tensor kk. That's all it is. Okay, and we are looking at, unfortunately, we're not looking at gamma omega k, we are looking at phi gamma minus phi omega k, phi omega k. This is what I'm looking at. Is it clear? Is at least what we are doing? I mean, not how do we do the next step, but so far is it clear?
Yes, sir.
Okay. Can I do this? Okay, so let's. What is the time now? 5:15, right? Are you guys okay with me continuing or what?
I'm okay.
Or do you want?
Yeah, it's fine.
Okay. Okay. So I'll just write this down. Not a big deal. So we'll be done actually. So 1 by k. We can do this, right? I'm just writing this. K equal to 1 through k. Sk tensor kk minus 1 by k. K equal to 1 through k. Omega tensor kk. This is clearly, I mean, you can actually see it. It's not, it's actually equal to, okay, so let me write, let me do this. I mean, can I say this is less than equal to oh, I'm sorry. This is wrong. This is wrong. I was after this. This is something else. So I'll just, kind of put this line. This is important. This is a very important step. Put this line. Can I say this? Gamma minus omega k. Okay, gamma minus omega k. This is this. Can I say this is this? Is this so? Let's say 1, 2. Is 2 okay?
Yeah. Yes.
1 is by definition. 2 is okay. Or why is 2 okay?
It's triangle inequality.
Yeah, triangle inequality. Okay. Triangle inequality. Can I say this? Can I say this? Why is this true? Why is 3 true?
Like there was this telescopic property of trace distance.
Not telescopic property. Telescopic property is no, what is telescopic property of trace distance?
Like if we have rho 1 tensor W minus sigma 1 tensor W trace
Oh,
distance,
yeah,
then it
okay.
is sum of rho 1 minus
Oh, okay.
sigma.
Nice one. So you're saying this is less than equal to what?
Yeah, rho 1, yeah,
Sorry.
rho 1 minus W1. No, the rho 1 should be common in both sides.
Oh, rho 1 should be common in both, huh?
Yeah.
So it's rho.
Yeah. So now we can.
So you mean this?
Yeah.
What is it? What is
No. Like rho tensor W minus sigma tensor W is the original thing.
Oh, rho tensor W minus sigma tensor W. What is this equal
Yeah.
to?
that is equal to trace distance between wait, I'll tell you exactly.
Yeah, take your time.
Yeah, like suppose if we have rho 1 tensor W minus yeah, this expression that is same as rho minus sigma.
Is it?
Yeah. Yeah.
Yeah, seems like that, though one needs to prove. Okay.
There was an exercise in build.
Okay. Yeah. See, this is actually orthogonal. This is like actually block diagonal. Yeah, this can also be thought of as block diagonal. So this is block diagonal. So you can actually show this. You can actually show this. This is just by the block diagonal nature, you can use the definition and show it. You can just use trace. See, root of, I mean, you have to be careful. Root of, so can you show this root of A tensor B is root A tensor root B? Then you are pretty much in good shape. Well, this is for positive semi-definite A and B, and in our case, it is true. So if you have this, then you can show that. I think this is true. Try and show it. Here it is very simple because you are essentially looking at a block diagonal structure, and you can kind of show this. Okay. So yeah. So what have I done? I've essentially shown that gamma minus omega k is 1 by k summation k equal to 1 through k sk minus omega, right? But I am after phi gamma minus phi omega k. Right? The question is, can I conclude this? Can I conclude this? Put a less than equal to because of the triangular inequality.
Yeah.
Can I conclude this?
CBTP map.
I'll give you 1 minute and think over it, because I want you to think over this. I mean, not just think over it, but actually argue it out, and then I'll come back. Okay, what do you think? Is this correct?
So we had some result like, I don't think, like if we take a partial trace, then the distance goes down, right? So that will not work.
Okay, say that again.
If we apply the partial trace, then that is a CPTP map, but that will reduce the element distance. So we can't use that.
So if I take the partial trace, I'm going to get Px and Qx, right? So
Yeah.
distinguishability, if I'm given two variables of P or X,
More, yeah.
as against to one variable with respect to X, right? Distinguishability of Px. So if you give me two variables and you ask me to distinguish, I'll be able to distinguish more,
Yeah.
better, which means
Yeah.
that the distance is more than
Yeah.
this.
Yeah, that will not help us here.
Also, remember that partial trace. So how do we, so remember, if I have two states alpha and beta, and I have a CPTP map E of alpha minus E of beta is less than or equal to alpha and beta. Now, partial trace is actually a CPTP map. You did this in the chapter 9. Partial trace is a CPTP map, which means if I take the pure state, if I take a pure state, so phi gamma minus phi omega, and I do the partial trace, that means I will be going down. So this is going to be gamma minus omega. So that means it is this way. Do you guys agree?
Yes.
Yeah.
So I can't do this. So all this work is bullshit. So all this thing that I did, right, is useless. Useless. So this is incorrect. So I mean, so I'll write only the correct inequalities in green. This is correct. This is correct. So that means I can't compare. Okay. Make sense? Clear so far?
Yes, sir.
Okay, great. Okay, but let's write down what is omega and sk. Then we'll get some idea. What is omega? Omega is root. So what I mean, suppose I mean some some weird. Let's look at this guy. I don't know. I wrote this. I mean, I should have written it just like that. But just let's just write that again. Okay. What is omega? Omega is root tensor n. What is sk? Sk is 1 by 2 power n r m equal to 1 through capital M root omega lambda xn of k comma m root omega divided by trace omega lambda xn of k comma m. So what am I looking at? I'm looking at the following. Omega rho tensor n minus 1 by 2 power nr m equal to 1 through capital M root omega lambda xn of k comma m root omega divided by trace omega lambda xn of k comma m. What do you think this is? I mean, I know it may be useless. It may be useless because I'm on the other side of the inequality. What is the point in dominating this guy? But let's look at this guy. Let's still study this guy. What do you think this is? Question is clear?
Yeah.
I claim this is another instance of the covering lemma. Why? Let consider the distribution, consider set X. Consider a distribution Px as trace rho lambda x. That's my distribution. What is my state alpha x? Alpha x is root omega lambda x root omega divided by trace omega lambda x. Is alpha x a state? Alpha x is definitely greater than equal to 0, no doubt about that. Sorry, this is rho. Alpha x is definitely greater than 0. Why lambda x is greater than 0? Definitely, alpha x is greater than 0. What is trace alpha x? Trace alpha x is trace root rho lambda x root rho divided by trace rho lambda x, which is 1. So alpha x is a state. Awesome. I have an ensemble of states now. What is summation? So x, px, alpha x, x belonging to x, I have an ensemble of states. What's the average state? Summation px of x, alpha x. What is this? Trace rho lambda x root omega lambda x root omega by trace rho lambda x. Sorry, this is not omega. This is not omega. What is this? This is summation root rho lambda x root rho. What is this?
It's just a row.
It's just root rho I root rho, which is rho. So which means this ensemble has average rho. So this guy is also an instance of the covering lemma. This is also an instance of the covering lemma. My states are different. This is my state, alpha x. This is my, the distribution, actually they're pretty much the same. This is my state. This is my distribution. This is my set. And this is tensoring. This is subsampling. So this kind of tells you that somehow these guys must be connected. Okay, it turns out that this identity doesn't work, but I can bound this guy. I can bound this guy using the covering lemma. So I can control gamma minus omega k. Now, how do I control the purification? Is the puzzle so far clear?
Yes, sir.
Okay, so it turns out, yeah. So this is where I came to, and I had actually I was doing this on my own maybe 2 years, 1.5 years or 2 years ago. I came to all these steps, and this is really where I ended up with. And I knew, okay, this guy is simple. The first term that we have done, that was evident to me that it was the covering lemma. It was the covering lemma. I gave an alternate proof of the covering lemma. So everything was fine except this step, and this was troubling. Okay, it's extremely troubling. I spent a lot of thoughts on this, and it turns out that you can show. This is not true, but you can choose your purifications. Remember, purifications can be. See, remember, if you rotate the reference space, it's still a purification. So if I choose, so I can take two states that are close. I can take two states. So let me explain this. So I can take two states alpha and beta that are very close, but I can choose purifications whose reference spaces are rotated so that phi of alpha and phi beta are far. There is no reason for them to be close because purification is not unique. Okay. So you can choose purifications that are far. That tells you, okay, possibly there are purifications that are close also. Possibly you can choose purifications that are close also. That's what it turns out to be. So it turns out to be that you can choose your purifications such that the following holds. Okay, so this is the thing. So you can show. Well, I have to be careful here, but essentially what I showed was that phi gamma minus um, phi omega k, obviously not less than equal to, obviously not, but it is less than or equal to the fourth root of, if you choose your purifications correctly, this happens to be true. So when you take the fourth root, remember it increases. These are all less than 1 quantities. So when you take a quantity that is less than 1, let's say 0.25, let's say 0.25, and you take the square root, you're going to get 0.5. So it's increased. So 0.25 is less than root 0.25. So similarly, 0.25 to the power 1 by 4. So clearly, this is not less than equal to just the distance between gamma and omega k, but less than equal to the fourth root of gamma minus omega k. How does it matter? If you can show this quantity at the bottom falls as exp minus n times some positive quantity, some positive quantity eta, then essentially this thing is falling as exp minus n by 4 eta. How does it matter? It still falls, right? So that's the idea. So essentially I could see that, okay, I mean, way it worked is that, okay, it is the covering lemma, but you need to do some more work to connect to the covering lemma. And I'm not sure if I'll do this part, but I wanted to show you the application of the covering lemma, and it's only this one small inequality that this is not trivial, okay? This comes out through some non-trivial inequalities that I did not do myself, but I had seen somebody else use it. It turns out it comes through some interesting inequality. There's a very good book by Bhatia on matrix analysis of almost a must for quantum information theorists. This is called matrix analysis, and that inequality was there in that book. But essentially, I could reduce the second term also to a covering lemma term, but not use in the standard way. You have to do some work because, I mean, the take home points here is that if the states are closed, purifications need not be closed, first thing. So that inequality is wrong. This inequality that we wrote is wrong. Furthermore, there are purifications that can be far apart because you can always rotate the reference plane. But it also turns out that there are purifications that are close. Obviously, they will not be very close. There is a fourth root cost you have to pay, right, in substance, because obviously you're adding more, right? So this guy, I mean, the purifications are more distinguishable. So this is the big story. For more details, the paper is there that does all these steps. But you saw two applications of the covering lemma. The state is non-trivial. The state, characterizations are non-trivial. But a very nice problem where you get, and what are the rates? Let's write down the final rates, right? So R plus C, they should be greater than S of this quantity, right? I mean, I'm just writing it down. This is a state. This is your R plus C, Km. That's the first term. And the second term gives you this. Because you have M, you get the following. S of rho minus S of lambda. These two are different, okay, by the way. So the difference between this can be communicated through public coins. That is your C. It is the two applications of the covering lemma. And just go look at it. I mean, if you remember, if you have alpha x p x of x, so I'm just writing. So this is alpha x, this is beta. Then beta tensor n minus 1 by 2 power nr m equal to 1 through capital M, alpha xn of m. This is small, I'll say exp. Actually, we showed the following: exp minus n times r minus s of beta minus x px of x s of alpha x. This is your covering lemma. Okay, I'm just writing it down. Plus some beta plus some eta, something like this. So if r is greater than this, then this term falls down. Okay, and that's exactly what I've written down. Okay, I'll have to connect the power once again. Okay. Questions? Thoughts? So that's it. No more classes. I have asked for the proctor. I should get it. I will not include quantum entropy. I will also specify the syllabus clearly today. Definitely will have all everything till the distance measures. After that, my current thought is that we will have typicality, because you did a homework and it's not that difficult. I mean, not that it's not difficult, but it's you did a homework, so you're more comfortable, and it's just an application of classical typicality. Will not have quantum entropy. Where's the book?
So like a quantum typicality would be there, right?
Yeah, quantum typicality would be there.
Okay.
Because it's an extension of classical typicality, really. And classical typicality, I think you work. I will send out some notes of my classical typicality, more fleshed out, if any of you are interested. Very, very clearly fleshed out all the elements. Everything till distance measures, purifications, CPTP maps, Schmidt decomposition, entanglement. I don't think I will have teleportation. I might not have teleportation and super dense coding. I mean, not difficult, but and gates, I don't think I'll have. I will specify this. Purifications, Schmidt decomposition, CPTP maps, tri-cross operators. I can have a revision session, not a problem. Distance measures, no entropy. Though, I mean, I'm not saying that no entropy means, I mean, some S of rho, you should know what is S of rho. I might do the following. I might say no packing lemma, but the HSW theorem, and only the covering lemma, no quantum measurement compression. This is my thought now. So you won't have packing lemma, but you will, I mean, just look at the HSW. I'll think about it. What I'm favoring now is distance measures, no entropy, quantum typicality, no packing lemma, no quantum measurement compression per se. But see, everything I did now, I mean, you might wonder, okay, I mean, no, all of this, are essentially small exercises in the, once you stay what's going on, it's all small exercises. So it's not bad to look at this lecture. It's actually useful. I mean, there might be some questions. Um, um, and I might include the covering lemma proof that I did, because that's not that difficult actually. But this is my thought, my take. I'm planning. I'm okay having it any day. I want to give you some days. Today is 23rd. 26, 27, 28. I think Srinidhi requested that 1 or 2 days he has exams. Other than that, it should be. I'm okay. I'm just waiting for. I'm just waiting for a proctor.
Yeah, like you said, you can have a review session, right?
Yeah, I can definitely have.
Okay, so yeah, that will be good.
Yeah,
If you can have it sometime before then.
yeah. Let me stop recording. Let me stop recording. Okay.